Welcome to all of you. Now we discuss Unit-2 2021 Biomathematics Semester 5 Mathematics Honors, University of Calcutta. Unit-2 question 4a. Let x star, y star be an equilibrium point of the following system: dt of x equal to fxy, dt of y equal to gxy, where f and g are continuously differentiable. Obtain the linearized system about x star y star, hence discuss stability of x star y star. Let x star, y star be an equilibrium point of the following system: dt of x equal to fxy, dt y equal to gxy, where f and g are continuously differentiable functions. Clearly, f of x star, y star equal to 0, g of x star, y star equal to 0 also, because x star and y star an equilibrium point of the system. Let us linearize the system 1 about the point x star, y star. Consider the most small perturbations u and v, both are positives, such that u equal to x minus x star, v equal to y minus y star. Differentiating 3 with respect to time t, dt of u equal to dx dt and dt of v equal to dt of y, because x star and y star are constants. Using 3 and 4 from 1, we get the value of dt of x equal to dt of u, f of x, y, f of x in place of x, u plus x star, in place of y, v plus y star, and dt of v equal to g of u plus x star, v plus y star. This system 5. By Taylor's series expansion of the function f about the point x star, y star, we get this f of xy equal to f of x star plus u star, x star plus u, y star plus v. Now, expanding this, we get f of x star, y star plus u del x of f at the point x star, y star plus v del y f at the point x star, y star, and plus dot 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 dot, neglecting second and higher order terms as u and v are small quantities. Similarly, gxy equal to g of x star, y star plus u del x g at the point x star, y star plus v del y g at the point x star, y star. Equation 7. Using 2 from 5, 6 and 7, we get using 2 here f of x star, y star 0, g of x star, y star 0. So this from 6, this f of x star, y star 0, and this 5 dt of u equal to f of this, so dt of u equal to this, so we get dt of u equal to u del x f x star, y star plus v del y f at the point x star, y star. And similarly, dt of v equal to u del x g at the point x star, y star plus v del y g at the point x star, y star. System 8. This system 8 is the required linearized system of the corresponding nonlinear system 1, that is the given system. In metric notation, we can write this system 8 as this matrix 2 by 1 column matrix, dt of u, dt of v equal to this 2 by 2 matrix fx, fy, gx, gy, that is means del f del x, del f del y, del g del x, del g del y, and this column matrix u, v. This matrix evaluated at the point x star, y star. The coefficient matrix, this fx, fy, gx, gy at the point x star, y star equal to j at the point x star, y star, is known as Jacobian matrix, variational matrix, or community matrix of the system 1. Now, the stability analysis. The characteristic equation of 8 this system, create this a11 minus lambda, a12, a21, a22 minus lambda, this determinant equal to 0, where a11 is the del del x of f, a12 equal to del del y of f, a21 equal to del del x of g, a22 equal to del del y of g. So we get quadratic equation of lambda, t square minus t lambda plus delta equal to 0, where t equal to a11 plus a22, that is the trace of the Jacobian j, equal to this, and delta is the determinant of j. So a11 a22 minus a12 into a21, and discriminant d is the t square minus 4 delta. The eigenvalues of this Jacobian matrix is lambda 1 and lambda 2. Lambda 1 equal to t plus root over of delta whole divided by 2, lambda 2 equal to t minus root over d whole divided by 2. By Routh-Hurwitz criterion, the necessary and sufficient condition for the eigenvalues lambda 1 and lambda 2 to have negative real parts are this trace t less than 0 and determinant delta is greater than 0. And next, hence discuss the stability of x star y star and the nature of these eigenvalues. We here list of this nature of the eigenvalues lambda 1, lambda 2, and the corresponding equilibrium points, nature of the corresponding equilibrium points. If eigenvalues lambda 1, lambda 2 real and negative, that is lambda 1 less than 0, lambda 2 less than 0, then equilibrium point x star y star is locally asymptotically stable node. The nature is this is the point x star y star, so this is the locally asymptotically stable node. And when lambda 1, lambda 2 real and positive, both lambda 1 greater than 0, lambda 2 greater than 0, the unstable node, so this is the point x star y star, and so this is the nature of this unstable node, this. And when real and opposite signs, that is lambda 1 less than 0 less than lambda 2, or lambda 2 less than 0 less than lambda 1, is a saddle point, which is also unstable, because this is the this line is stable, but to this point x star y star, and this is the unstable away from this point. So this is actually unstable saddle point. Complex with negative real parts, that is lambda 1 and lambda 2 eigenvalues are alpha plus minus I beta, where real part alpha is negative, then stable focus. So this point x star y star, so the stable focus is this, so moves to this point equilibrium point x star y star, this trajectory. Complex with positive real part, that is lambda 1 comma lambda 2 equal to alpha plus minus I beta, with alpha greater than 0, unstable focus. So this from this x star y star equilibrium point, and this trajectory goes out from this equilibrium point. And if these eigenvalues are purely imaginary, that is lambda 1 comma lambda 2 equal to plus minus I beta, and beta is real, this linearized system have a center, but this center is this, but original nonlinear system have a center or stable or unstable focus depending on the nonlinear terms. And these are the natures of these equilibrium points. Next question, question 4 part B. State the basic assumptions of classic Lotka-Volterra model for predator-prey system. Write the model equations, discuss the stability of the system about the non-trivial equilibrium. Actually, this question is this basic assumptions of the classical Lotka-Volterra model. Prey will grow exponentially in the absence of predator. Number 2, the effect of predation is to reduce the prey's per capita growth rate. Number 3, prey's contribution to the predator's growth rate is proportional to the available prey as well as to the size of the predator population. Number 4, in the absence of prey, the predator population decreases exponentially. And corresponding model equation is this, ddt of x equal to x bracket alpha minus beta y, and ddt of y equal to y bracket minus gamma plus delta x, this system 1, where alpha beta gamma delta are positive parameters, xt and yt depending on the time t are respectively given by the prey and predator populations at time t. Now for equilibrium point, say x star y star, this ddt of x equal to 0 equal to ddt of y at this point x star y star. So from this ddt of x equal to 0 gives this implies either x equal to 0 or y equal to alpha by beta, and from this ddt of y equal to 0 gives y into bracket minus gamma plus delta x equal to 0, and that implies either y equal to 0 or x equal to gamma by delta. If we choose x equal to 0 here, then y equal to 0 here from this second equation. So equilibrium point is this E naught equal E naught this 0 0 trivial equilibrium point, and this if we choose x is here, so x star is this gamma by delta and y equal to alpha by beta. This is the non-trivial equilibrium point, coexistence equilibrium point. Interior equilibrium point is this. Now variational matrix J, there is fx, fy, gx, gy, set f equal to this, g equal to this from the given equation system 1. The right hand side is f, and this second equation, this g. So del fx, del f, del x, del f, del y, del g, del x, del g, del y. Find all these quantities and put here. This two, we get this 2 by 2 matrix alpha minus beta y minus beta x delta y minus gamma plus delta x. At this equilibrium point E naught 0 0, j at the point 0 0 is alpha 0 0 minus gamma. The eigenvalues are obviously diagonal elements alpha and minus gamma. Alpha is positive and gamma minus gamma is negative, because gamma alpha are all positive quantities. So E0 is a saddle point which is unstable equilibrium point. Next, at the point E star coexistence equilibrium point, this at this point j equal to 0 minus beta gamma by delta alpha delta by beta 0, this 2 by 2 matrix. So we can not find not a diagonal matrix, a principal diagonal you got 0, not a upper triangle matrix, not a lower triangle matrix. So we use here Routh-Hurwitz criterion for that. Actually we want to find the eigenvalues, this corresponding this 0 minus lambda, this 0 minus lambda corresponding determinant equal to 0, so quadratic in lambda. So we get two eigenvalues lambda 1 and lambda 2 equal to plus minus I root over alpha into gamma. Eigenvalues are purely imaginary, hence the interior equilibrium point E star is a center. Next question 5a. Consider the nonlinear system ddt of x equal to x bracket 2 bracket 1 minus x by k bracket close minus 3y by 1 plus x bracket close, and second equation ddt of y equal to y into bracket minus half plus x by 1 plus x bracket close k greater than 0. Find the equilibrium points and discuss their stability nature. For equilibrium points, this ddt of x equal to 0 equal to ddt of y. So from the first equation, this ddt of x equal to 0 implies either x equal to 0 or this factor is 0. So from the second equation, this ddt of y equal to 0 gives either y equal to 0 or this from this factor this equal to x by a1 plus x equal to half. So equilibrium points are this x0 y0, so 0 0. If we put x equal to 0, so if we put y equal to 0 here, so y equal to 0, put here y equal to 0, so we get value of kx equal to k, so e1 k0, and from this we solve this x equal to 1, this x equal to 1, put x equal to 1 here, we get y equal to this. So we get three equilibrium points E naught, E1 and E star. The feasibility of E star, obviously this quantity, if quantity is positive, that is 4 by 3 bracket 1 minus 1 by k is greater than 0, that is k is greater than 1. Jacobian matrix J, this fx fy gx gy 2 by 2 matrix, find this fx fy gx gy, where f is this fxy a function, this right hand side part and gxy equal to this. So after calculating, we get this 2 by 2 matrix. At this point, E naught, at the point 0 0, put x equal to 0, y equal to 0 here, j, then 2 0 0 minus half, this diagonal matrix. So eigenvalues are 2 and minus half. So E naught is a saddle point because this 2 is positive eigenvalue, so and which is unstable. At E1, at the point k comma 0, value of Jacobian j at the point k0 is this minus 2 minus 3 k by 1 plus k, 0 minus half plus k by 1 plus k. This is the upper triangular matrix, so diagonal elements are the eigenvalues. So these and these are eigenvalues, and this table is the negative. So if this eigenvalue is negative, show the stable. So for that, this condition is that is if k is less than 1, that is if 0 less than k less than 1, then this E1 that is k comma 0 is stable equilibrium point, actually locally asymptotically stable. Unstable if k greater than equal to 1. Next, for coexisting equilibrium point, this E star 1 comma 4 by 3 bracket 1 minus 1 by k, value of j at this point E star, this value matrix is this 1 minus 3 by k minus 3 by 2, 2 by 3 bracket 1 minus 1 by k comma 0, this 0, 2 by 2 matrix. And so this not a diagonal matrix, not a upper triangular, not a lower triangular matrix. So so we find trace of this matrix, this either find this or you can find the eigenvalues, these characteristics and so on. And trace of j star is this sum of the diagonal elements, and the determinant of j star equal to this into this minus this into this. So this. So E star is stable if this trace is negative and determinant value is positive. So if this is negative and this is positive, that is if 1 less than k less than 3. Next question, 5b. What is meant by bifurcation? Discuss saddle bifurcation for the system dt of x equal to mu minus x square. Mu is the parameter. A bifurcation occurs in a nonlinear dynamical system dt of x equal to fx, mu, when a small change in the parameter mu results in a qualitative change in trajectory structure of the system. The system is said to have a bifurcation at mu equal to mu c, particular value of mu, if there is a change in the number of steady states and or in stability behavior of the steady states when mu crosses the value mu c. Saddle node bifurcation for this system. This system is this equal to fx, say for steady state x star dt of x at the point x star equal to 0. So mu minus x star square equal to 0. So x star 1 comma 2 equal to plus minus root over mu. Now case 1, when mu is less than 0, then x 1 comma star equal to plus minus I root over mu. This I equal to root over minus 1, this complex number. So these equilibrium points are purely imaginary numbers. So there is no steady state in this case. Case 2, for mu equal to 0, then x star equal to 0 is the only steady state. Now f dash 0 equal to 0, so we cannot find the nature, cannot say the nature about this stable or unstable by this sign convention notation. For this we use the graphical method and observe that from the graph x star equal to 0 is semi-stable. Actually this is the semi-stable nature. In case 3, when mu greater than 0, then x1 comma 2 star equal to plus minus root mu, and there exist two steady states, root over mu minus root over mu, and f dash root over mu equal to minus 2 root mu. This is less than 0. Then x star equal to root mu is stable, and f dash root of minus root mu equal to 2 root mu, this is greater than 0. Then x star equal to minus root mu is unstable. And page portrait is this given by when case for mu less than 0, this x, and this is the dx dt vertical axis. So this corresponding graph is this this graph. For this graph, mu minus x square equal to fx. When mu is negative, you can easily draw by Desmos app or any other app on net. And this for mu equal to 0, with this the portrait this x-axis, this corresponding vertical axis dx dt, and corresponding point mu is this. And for this, from the right hand side, this approach to this point, so this stable, and left hand side is unstable, so this is the semi-stable. And when mu greater than 0, for this case graph is this, and this point minus root mu is unstable, but root mu is stable, going from both sides, going to this point from both sides. Bifurcation diagram, this curve fx equal to mu minus x square determines the position of the steady state when mu varies negative to positive. This is the mu axis, horizontal axis, and vertical axis extra critical point or equilibrium points, and the system exists negative to positive. For negative mu, there is no equilibrium point, and for this mu equal to 0, this only one critical point, this x star equal to 0. And when mu is greater than 0, we get two critical points, this and this actually, and this and this. This is the positive critical equilibrium point, and this negative critical point, this positive and this negative. And this is the positive equilibrium point is stable, and so this is the positive equilibrium stable, and this negative equilibrium unstable. So this branch, dotted line, is the unstable branch for this unstable branch for this equilibrium point, and for this equilibrium point is stable branch, so we get this stable branch is this. And this, the upper branch of this curve gives the stable equilibria, and the lower branch gives the unstable equilibria. Clearly mu equal to 0 is the bifurcation point of this, is the called the saddle node bifurcation. Actually this is the supercritical saddle node bifurcation. And we can get another cases when mu fx equal to mu plus x square, then we get subcritical saddle node bifurcation. The graph is this in this part, negative part of this, this the subcritical saddle node bifurcation for mu fx equal to mu plus x square. So this is the bifurcation diagram. Next question, question 6. Consider the model following bacterial growth in chemostat is this, by using this quantity, this non-dimensional system, equilibrium points, dimensional system, determine the stability of biologically meaningful equilibrium points, and so on, so on, so on. Actually, this question already answered already in 2023 Unit 2 question number 6. So please see this video 23 Unit 2 for this answer of this video. And next question, part B, sorry 7, question 7. What is a compartmental model? State the basic assumptions of Carmack-McKendrick SIR compartmental model, draw the flowchart and write the model equations, find the basic reproduction number, determine the condition for which the epidemic spreads and infection dies out. Compartmental model, actually in an epidemic model for infectious diseases, total population is assigned to be 3 compartments or classes or chambers: susceptible S, infected I, and recovered R. We assume that individuals in each compartment have the same characteristics. Hence, an epidemic model is also known as compartmental model. And for the second part of this question, Carmack-McKendrick SIR compartmental model, already we have answered this in question 2023. So please see this video 23 Unit 2 question number 7B. Thank you for watching this video. This completes Unit 2 2021.